She received her PhD in electrical engineering from University College Cork, Ireland in 2013 in the field of the great integration of marine renewables. After one postdoc at the University of Nantes, France, in the same topic in 2014, she expanded her research field to the optimization of the design and the energy management in power systems during a Marie Curie fellowship. Since 2015, she has been a tenured research fellow with the National Center for Scientific Research at IETR lab. Her research interests cover the modeling of electrical networks and the optimization under uncertainty of power systems design and energy management from a wide range of tools, going from the mathematical optimization to AI tools. Today, she'll share her recent work from the IETR lab on decentralized smart charging for energy vehicles and AI-driven energy management models. Please join me in welcoming Dr. Blavette.
So I'm very glad to be speaking in front of you today. As has been introduced, I will focus my on the decentralized smart charging of electrical vehicles, and especially large-scale fleets of electrical vehicles. So first of all, well, that's the plan for today. First of all, I will try to introduce my different organizations, how it works, also my main research axis, and then we'll go to other, sorry, it's in gray already, but we'll go to other topics that you cannot maybe see very well in the screen here, looking on energy management. A little bit of context. The two problems that we had to solve, and for which I will tell you the long journey we had to go to different decentralized methods coming from adaptive multi-agent system to bandits and to combining them in the end. And if I have a little bit of time, I will try to tell you more about the AI-based security assessment of power systems, maybe a little bit of cybersecurity. So as was mentioned, I'm a senior CNRS researcher at IETR lab. We have a wonderful campus. You do also have a wonderful campus in Kilolugen, and I could see that. We're located in the west of France, in Rennes. And I'm part of ENS Rennes. So ENS, what does that mean? It's an economic stipendia of Rennes. There are 4 ENSs in France. The first one was created right after the French Revolution. Every century, one ENS that is created, and the latest created 10 years ago. Big celebration for the anniversary. So that's the last 20th century ENS. So Ines will tell you more about what that is, because I know that's coming from one country to another, higher education system could be kind of confusing. ENS, they are accessible through a highly competitive national contest that people take after 2 years of intensive preparation that are called preparatory schools. And you have different specialties in the different ENSs. One of our specialty in Rennes is mechatronics. So our students work both on electrical engineering, mechanical engineering, but also physics. They also have material sciences and chemistry as well. The big motto of ENSs, for all ENSs, is to train future researchers and future lecturers. So we try to train them for research by research, which means that we have a lot of different research projects in the curriculum, in the syllabus of the different training courses. And our students that are self-funded have different types of projects to do around the years. So they have small research projects where they once a week in the lab to work with us during 8 weeks, for instance. We do that either on Rennes labs or also with distant labs with collaboration mostly with ENS colleagues. And we also have different internships going from 2 to 4 months internships at lower levels, like at the end of the license or beginning of master degree, after final year internship level for 6 months, and also pre-doctoral training where we send them anywhere in different labs so that they can have a taste of research and confirm their envy to embark on a PhD. So that's for us. That's for while sending our students. We're always happy to have your offers coming in and transfer that to them in case they're interested. But we also welcome other students. Also, we have different ways of doing that. We can have the parallel admission, for the main ENS training path in parallel to the national contest. We have different master degrees, one on complex system, another one on smart energy that we run with the Central Supélec, which is a French higher engineering school for electricity and power systems. And we also welcome, of course, PhD students for short to long stays. Regarding the lab, IETR, which stands for Institute for Electronics and Digital Technologies, we are about 350 members before, including 160 PhD students and postdocs. We have very different topics ranging from energy to digital sciences and communication, health, environment, and mobility. And per year, to give you an average figure of the lab, we have 40 PhDs, 75 new projects, 10 patents, and 1 startup. And yeah, IETR is part of this big umbrella organization that is CNRS, the French National Center for Scientific Research. I'm talking about CNRS here because the national contest for CNRS is opening very soon, in case there are people interested here online. CNRS offers rare possibility to have 100% research position that are tenured, and for which you can apply through strong research projects at first stage, and then maybe at later stage, if the first one is validated, an audition. And the deadline for submitting the research project is in February. So if you're interested, I would strongly recommend that you do a screening of the landscape of research in France, try to connect to the different labs in which you might be affected, you might be assigned, and try to build up your research project much in advance.
You need to have a PhD?
Yeah. Okay. And so maybe downscaling step after step. I told you about the lab. Now I will tell you just to finish about our team. So our team is called Sciences. We were happy to find this name because we could put ENS in the middle of it. So that's our brand. We're part of the Smart Energy Department of IETR, a newly created department. And it stands for Energy System and Sustainable Electrical Transducers. We're about 5 to 10 researchers in my team, 11 in the lab. We also include people in the control theory community working on energy. And our main research axes are around the methods for optimizing the energy management and the design of power systems. We do also modeling of energy systems, whether it be stochastic, multi-physics, etc. We also work on the eco-design of electrical vehicles and power electronics, a new concept for actuators, energy conversion. And last but not least, we do also prototyping and digital and analytical validation in our lab. So maybe to finish this part of the introduction, just to relate or maybe list my main interests, I would say, in terms of research. I work on the design and or energy management optimization of energy systems, whether it be large-scale smart grids to microgrids powered from many different types of renewables, including marine renewables. Also, I'm interested in cyber physical systems such as data centers powered from renewables. I do also modeling for power system studies, for instance, looking at the optimal granularity of specific models for different specific applications. AI-based modeling for faster security assessment. Maybe I have some time to talk about it. And also introducing new concepts in the energy management of electrical networks that have been creating or really flexible contract power and multi-energy system and cybersecurity, which are part of new upcoming projects. So going now to the more technical details and the focus of this talk, which is the the large-scale EV fleets energy management. So the first part will be on the first problem that we had, that we started with the the BRP imbalance problem. So we'll tell you more about this in a second. I will completely skip the context where we all know that we have to reduce our gas emission and we're going through a massive electrification, and so we are having electrical vehicles and large-scale EV fleets coming in. Because as we know that we have EVs that could be controlled by different operators, could be the owners themselves, they want to have the EV fully charged, sufficiently charged before departure. We could have DS or TSO trying to manage the EV for different needs, for removing congestion, for frequency regulation, etc. We can have the VRPs as well that are financially responsible for the imbalances in the network. And so these different goals will have to tackle large scale of EVs, which means that we need decentralized methods to reach individual, local, and global objectives and goals. As I said, it was a longer journey to try to find interesting decentralized methods. In the end, we found a combination of two methods could be interesting, which are AMS, adaptive multi-agent systems, and multi-arm bandits. It's an RL method. I will discuss that later. These two methods are developed or are studied in two different groups with whom we have collaborated. The first one is the IRID lab in Toulouse, developing the adaptive multi-agent system theory. And the second one is Orange, where we have in Brittany a strong research center on AI. So Raphael Ferro is a research professor there and is working with us for bandits. So for the problem, the global problem, is the smart charging of EV in the presence of photovoltaics, renewables with photovoltaics, among others. The first problem that we've tackled in the initial problem was the BRP imbalance reduction, the reduction between the imbalance between production and consumption. And the second problem was to absorb the excess of the electricity. So it's kind of similar, but it has some sort of small differences. In the second problem, we want to minimize the cost of energy. And in the first and second problem, also want to satisfy the grid constraints and the mobility constraints. And in the second problem, we add on the top of that some fairness, but I will detail that a bit more later. So for the case study, at first, we wanted to have a look at this BRP problem, where a BRP is a balanced responsible party, which has which is in charge financially of the different imbalances in the network. So it has a perimeter, and it tries to forecast the production and the consumption, and it's penalized whether there are deviation. So we might expect some error coming from the forecasts, as they have forecasts. In our case, we chose a case where there would be a PV upward production in the beginning of the first period, and there are 15-minute imbalance periods that are considered, and then there would be a PV underproduction based on that, and the EVs would have to react to minimize the error. One hypothesis that we had is that the error would always be penalized. That's what happens in some of the French islands, where they had really to be very stringent on grid cost requirements. So any deviation from what is forecasted is penalized. That might not be the case for BRP at the current time. Might be something that is envisaged maybe later for the future. So the BRP the BRP objective function is to reduce the imbalance between what is actually forecasted and what is actually seen when it's produced. And we do a planification on what is actually forecasted based on what is actually happening plus a nearer term. For the case study, we use the European low voltage feeder as an example with 55 EVs, 55 loads, and we've tried to have a broader, a bigger network by adding different sub-districts like this. They're actually a low voltage feeder. We've had 9 sub-districts, so a little bit less than 500 EVs, and the goal was also to avoid a congestion on this higher voltage transformer here. So current condition to be avoided. For the network equation, so you can see, or maybe it's a bit fuzzy, you can see the network equation here. For the AMAS-based method, we have used PandaPower to solve the actual equation, because the AMAS-based in a real-time method that's actually would get, if it were deployed in real life, would get data from the field. So we use PandaPower to do that. And for the distribution operator requirement, I can see here we try to avoid current and voltage condition. So of course, you have to satisfy the mobility needs with a SOC that is higher than a certain SOC for each different EVs. They can have different SOCs for each of them. The charging constraints also are more or less homogeneous, and you have to add the battery equation with some losses in it. So we have a linear losses here. So to have a lower band on the costs, we've cast the problem as a MILP, where we've used a small angle approximation and a unit voltage approximation as well, to giving these linearized power flow equations. And MIRT is of course interesting because it can give some sort of a lower bound, but it's well, it has a prohibitive computing time, of course, even for deterministic problems, which we have used here. We don't have used any stochastic MIRT form, but also it's also centralized, so you can have privacy and scalability issues, of course. So based on that, we see that MIRT here can give us some hints, but we need a decentralized look. That's where adaptive modulation system comes. So that's maybe a short introduction. It's reproduced and adapted from a tutorial that was done by my colleagues in IRIT on the theory of the system. The little short summary of so AMAs, they are used to simulate, design, engineer complex systems. But what are complex systems? I hate normally putting big bunch of texts on slides like this, but I mean, this definition here was very nice, so I kept it. It's from von Blavette. He wrote a book called General System Theory, and it still applies to what we can see today. So he said, while in the past, science tried to explain observable phenomena by reducing them to an interplay of elementary units investigated independently of each other, conceptions appear in contemporary science that are concerned with what is somewhat vaguely termed as boldness. That is, problem of organization, phenomena not resolvable into local events, etc. In short, system of various orders not understandable by investigation of their respective part in isolation. To complete with that, conception and problems of this nature have appeared in all branches of sciences, irrespective of whether inanimate things, living organism, or social phenomena are the object of study. So here, I like very much this video where you have a bench of fish and there is a big fish trying to eat some of the little fish. And the phenomena is it seems very complex because I mean there is a circle surrounding the fish and trying to scare him off, more or less. I mean, it goes away. Still, the little individual fish have very little information, very little intelligence as well. So you can see that complex phenomenon arise from the interaction of many smaller units. So that's typically what we would call a complex system. So now I've told you that multi-agent systems are here to model, engineer, optimize complex systems. Now, what are multi-agent systems? Here, that's you can see a bunch of references, very good books in the field. I could give you many different definitions, but I've tried to retain the most consensual ones. Colin, for instance, says that a multi-agent system is a macro system made up of autonomous agents who interact in a common environment and potentially to solve a common task. So it's a very short definition. Ferber, who has also a very consensual definition, says that in a more formal way, that a multi-agent system are a set of entities C plunged into an environment E, a set of agents A which are included in C, a system of action or operation, allowing each agent to act in E, and a system of communication between all the agents where they can send messages, they can broadcast a message. That's defined by the communication system. Also, the organization O, which structures the agents into different roles and different functions. And possibly you can have users like human interacting with a multi-agent system, and that could be identified or identified as one of the agents. On and on, you have many different definitions of multi-agent systems, but there are a few key properties, I would say, that are, well, I would say, global and common to all of them. They are cooperative, they are autonomous, that's the biggest consensus on that. They can be very reactive or cognitive, meaning that they could have very reflex-like answers, or they can have more sophisticated answers to different stimuli in the environment. There is this paradigm of locality where an agent has a given neighborhood, which could be a geographical neighborhood or a functional neighborhood, and they would receive information only from that neighborhood or send information only to a given neighborhood. So they don't have the knowledge of the entire system, they will only have a fraction of the knowledge. An agent can also be proactive, where how can I illustrate that? If there is a problem in the system, maybe agent would be contacted to to solve a certain kind of problem. But they also have to be proactive to look if the system is functioning in a normal way. So that's proactive means here. And so adaptive multi-agent systems, AMS, they come from the theory of multi-agent systems. They are also inspired from natural organisms, and they are based on self-organization. Self-organization means that if the system is engineered properly, you can have an emergence of a global desired behavior only due to the individual interaction between the different agents. Here in AMS, what they use is a concept of criticality. The criticality is a distance of an agent to a given constraint, a given objective. And by sending the different criticalities and each agent assessing the criticality it receives and its own, trying to reduce the maximum criticality, then there's a propagation that in the end should relax the system and would in the end minimize the overall criticality of the system. So there are very different ways to identify a problem. We can use a physical identification and agentification of the system, meaning that, for instance, here in our core system problems, we have a line that becomes a line agent and so on and so forth. That's what we have used. But I thought it would be interesting maybe to tell you about other types of agentification process. In a project that was done by my colleague in IRIT, they were working on airplane design, so involving many different disciplines, like aerodynamics, mechanical engineering, etc. They have identified a problem of this airplane design problem as all the models, all the different decision variables, all the different constraints and objective functions were agents. And they had to talk to each other to try to meet all the constraints, to maximize or minimize some objective function and so on. And so that project was ID4CS, Integrated Design for Complex System. It was done in collaboration with Airbus, among others, the School of Mine in France, Zafar, etc. And they had very interesting results. So two approaches for agentification of the problems, but still in all these approaches, both approaches, each agent is responsible for solving one part of the problem. That's the main approach. But the challenge is to find the right heuristics for the inner action of the agent. He did the right heuristics for communicating between different agents and also to optimal tuning of the hyperparameters. So coming back to our study, what we did is to define the criticality of the different agents. As I said, we have used physical identification, where actually all the lines become line agents, and all the different buses become bus agents, and the electrical vehicle become electrical vehicle agents. For the line and the transformer criticality, we have used a linear criticality where it is equal to 0 if the current flowing through a line is lower than the threshold, and then it increases materially if the current is above a given threshold. This type of criticality can lead to oscillations in the system. So we've added a memory term where the actual criticality is a function of the criticality that is seen the instant before, plus this criticality here, that is the linear criticality according to the present instant. And then you have two hyperparameters, one hyperparameter and the other one as 1 minus the first hyperparameter that are here to control the response in terms of oscillations. The bus criticality is done in the same way. There is 0 criticality if the deviation from the voltage is within a certain bound, a low bound, I would say. And then you have an increased criticality as long as there is deviation above or below that bound. Still, you have the memory term here that appears, plus the weighted sum between the criticality that is seen in instant before and the criticality that is seen at the end of the given instant. And for the BRP, it's a bit different. You just see that the criticality is the difference between the power that is forecast minus the power that is actually seen divided by the period that is the time remaining in the imbalance period. So the closer we are to the end of the imbalance period, the more critical the BRP might get if it hasn't solved its problem so far. And still you have the parameter that is K BRP. And for the EV criticality, it's based on whether it would be able to charge efficiently at full power before departure, without considering any congestion at all. Based on this, we can define the power of each electrical vehicle plus a memory term, and that includes the maximum criticality it sees at a given distance minus the maximum antagonist criticality it receives from the environment potentially. Because in some cases, it could receive two contradictory orders, either charge or discharge. So we try to weight the two objectives with a sum here. And of course, it's limited by the capacity, the power capacity of the electrical vehicle. So for the algorithm itself, there are three stages in agents: the perception stage, the action, the decision stage, and the action stage. For the perception stage, then the agent would receive all the different criticalities in the network. It would calculate its own. For the decision stage, it calculates whether the criticality received by the environment are higher than its own criticality. And then it would define what is the most critical agent in the neighborhood, whether it is itself or whether it's neighbors. Then we would have other things to calculate, like the labels. Is the criticality, for instance, the congestion in a line due to the fact that we're drawing too much power or that we're exporting too much power? So it would calculate that as well, or receive information from that. And based on that, it would, at the action stage, define its own power. So for the results, we have compared our strategy with different strategies. The first one is the naive and control strategy. Everyone starts charging their EVs as soon as they arrive. The MILP strategy, which is, as I recall here, deterministic. It knows the future, it's centralized. So of course, we have lots of scalability and privacy issue compared to the AMAS, which we have called Adenis here in the graphs you'll see. And when we compare, we can see that we have relatively good performances. We have 4 here imbalance periods for which the MIP finds a feasible solution. So there is 0 imbalance at the end. The AMS managed to find a good solution, very close to the MIP, whereas the uncontrolled charging has a very poor solution. And regarding the constraints, we can see here that with the uncontrolled charging, then we have a congestion, whereas the AMAS is following very closely the MILP solution here. In terms of results, the computing effort is very low, which is interesting for real-life deployment. As you see maybe here, the agent processing time per iteration, so it could be in the temporal resolution that you choose, it could be either minutes, seconds, 10 minutes, whatever. It's a fraction of millisecond almost the time, because they use very simple heuristics. So we can see here that for real time, also real life is in pink here. It's completely constant in terms of computing time, regardless of the number of agents. The same thing for the memory, which remains very low. But AMAs are also interesting for simulations, and have been used in simulation for many different complex systems, like transport system, for instance, because we have very reduced processing time and memory usage for the simulation. Here we can see one here in red, the MILP solution that increases a lot, whereas AMAS starts at a higher level, but then has a linear trend more or less for the simulation. And then when you arrive at around 1,000, 900, 1,000 electrical vehicles, then the computing time for the AMAS is lower than for the MILP. For the memory, that's something different. The memory for AMAS is very low compared to the MILP, as you can see here for simulation. Here I'm showing the result without considering the power system simulation. It's not, but it is included in the MILP, but not for the AMAS. Here I show something that includes both of them, because we wanted to extrapolate to see if, it's not showing well here, but here we have recorded all the processing time for different scale of the number of EVs. And we wanted to know when we included the time that was taken by Panda Power, for instance, to run the power simulation, what would be the influence of that on on the comparison with the MILP. So you can see that once we take the memory time for the MILP, that will constrain the computing time, we arrive at more or less the same conclusion, where we have where AMAS would be better in terms of computing time than MILP for about 1,000 PBs. So that was nice. We had good results on that particular part, but then we wanted to test the robustness to uncertainties through a pseudo-stochastic analysis, where we wanted to have a look at the impact of different uncertainties on the objective and on the constraints. So for that, we have used different scenarios where we took the planned irradiance and to which we've added an error term. So in terms of error, we have used autoregressive model of order 1 to model the error, as it is well known in wind energy, but also in solar. And the error, the noise follows a Gaussian distribution. So for the objective function, we see it varies a little bit, but still the order of magnitude remains kind of good. The problem is much more with the constraints, for which we have 50% of violations when we have uncertainty applied to the problem. So in that case, it's clear that we can have good results, but the tuning of hyperparameter wasn't robust to the uncertainties. So we had to include that much better in the system. And for that, we wanted to introduce bandits. But to come back to bandits, which was something that we didn't know at the time, we wanted to go to something more conventional in terms of problems. So we have used a second problem, which is a PV peak absorption, considering grid constraints. So here, to summarize this problem number 2, it's just a smart charging of EVs in presence of photovoltaics, but here to absorb the excess of PV production peak, with EV owners wanting to minimize the electricity bill and satisfying grid constraints like current and voltage congestion. Plus they have mobility constraints, and on top of that, adding a little bit of fairness. Maybe to give an idea of the scale of the problem, we have done some very simple calculation based on the perspective for France in terms of energy mix. Here, that's an extract from the energy pathway to 2050 by the French grid operator RTE. They have different prospective scenarios ranging from fully renewable to having massive integration of nuclear. And this one, the N2 scenario, is an intermediate scenario. In that scenario, we have about 90 gigawatts of photovoltaics. And how does that translate into a worst case, I would say, summer scenario at noon, when we have peak power production? We have to define what is the actual production that we could get at this time. How we did that? We just had a look at a very sunny day in France, maybe 2 years ago, where we had about 8.5 gigawatts of actual production, whereas the installed capacity was 15.5 gigawatts. So that gives us a ratio of about 54%. And we could imagine that maybe by 2050, we will have larger PV farms that will be well maintained, that will have less shadow than rooftop solar and etc. So let's say we have a production of 2/3 of the installed capacity. So that's 66% of 90 gigawatts. We get 60 gigawatts, and we do the same calculation for nuclear. 80% of availability. We have offshore winds, 18 gigawatts more. We assume that maybe it's so sunny that there is no wind. We do not have wind energy. That's a basic assumption. Then we have hydroelectricity, adding 5 gigawatts more. And for the load, we say that it might be 20% more than what it is today because of increased electrification, air conditioning, etc. So 60 gigawatts for consumption. So we end up with an overproduction of 54 gigawatts, which is about 9 million vehicles starting at 60 gigawatts. That's about 24% of the national park of vehicles in France at the moment. We have about 38 million vehicles. So it's a sizable fleet, right? We know that not only one operator, not only one aggregator, for instance, will have to manage this problem, but still it's not unbelievable to think that there won't be thousands of aggregators. So each of them will have to handle a sizable problem, a very large scale problem. And so for this, there is a need as well for decentralized method, and that's where we have applied our AMS bandits-based method. So a very short introduction to multi-armed bandits, which is maybe more detailed than the one that has been presented 2 days ago at KU Leuven. So I'll go a bit more into detail in there. And it's again reproduced and adapted from a tutorial that was given at the KDD International Conference a few weeks ago by my colleague Rafael Ferro here in Bold, who's an expert on bandits in Orange. So multi-armed bandits, where do they come from? Where does the term come from? It comes from what you can see here in Casino. You have this one-armed bandit, you pull the arm, you get whatever you get, but you lose a lot of money. But that's where the terms come from. If you have multiple one-armed bandits, you might be willing to win as much money as you would like, and then you have to choose which arms you will actually post. So that's a multi-armed bandit problem. And we can cast that kind of problem to many different problems in real. Multi-armed bandits, they are a classical reinforcement learning theoretical framework. And we could say that RL more or less is divided into multi-armed bandits and a Markov decision process based RL, like TQM, PPO, etc. When to choose bandits over MDP-based methods? Basically, it's when there is no reason that the optimal policy would change based on the played arm. For instance, to give you an example, if you play Go, if one of your adversary changes something on the chessboard, then you have to change your policy, which is not the case. Here, bandits wouldn't work. But if the optimal policy doesn't change according to the played arm, then you can use bandits. And bandits are able to tackle a large class of problems, which are non-stationary. They could be contextual. They could be structured bandits to tackle different problems. Combinatorial bandits as well. So there is many different possibilities. And if you are interested in that, there is the very good book by Sutton and Bartlow that I show here as a reference. It tells a lot about bandits, about bandit theory in first judges. So why using bandits instead of MDP-based reinforcement learning? So if you have a mole problem in your garden, you may have different possibility to get rid of that problem. Heavy machinery, I would say, or more simple tools like this. And bandits are the more simple tools that you can use to solve the problem of reinforcement learning. What you could get as expected gains by using bandits over MDP-based tools is that it's better in cold sort. That is, if you have no information whatsoever about the environment, then bandit-based tools will converge quicker in a more faster than MDP-based other methods. So it could be interesting, especially if you want to preserve privacy. It's also not expensive in terms of computational tools and costs. That's why it was attractive to us at the first time, because it's very compatible with AMS. That could be more feasible in real life environment. And then you can have theoretical guarantees that could guarantee some sort of robustness to unseen problems. And it is very important to have a trustworthy AI for critical systems that are, for instance, power systems. So an agent's goal is to maximize its cumulative reward over a given horizon that could be finite, infinite, known or unknown. Maximizing the cumulative reward also means, in terms of bandit framework, to minimize one's regrets. I detail that later. So each bandit would have, after an action is pulled, a random variable, a random reward that would be based on a probability distribution that is unknown to the bandit itself. It will have two estimates step after step. So it's based on unknown probability distribution with an unknown mean UK. So for each state that the environment gets, the bandit will have a chosen norm. So S0 is the state, KT is the arm, and then based on the state and the arm that has been played, the environment will get a reward. And here is the expression of the regrets over horizon T, capital T. It's a maximum of the mathematical expectation of the sum of the reward that would have been played if that would have been obtained if the optimal arm would have been played all the time, minus the reward that is actually given for the different arms that have been played over time. So the goal of that, of course, is to choose the best action, the best arm or set of arms, KT. So at first, the best arm is unknown. So the bandit is faced with the exploration versus exploitation dilemma. It has two questions: whether or should I continue with the current best arm that I have identified, that would be exploitation, or should I test or sample more arms in case there are any better arms that I haven't identified yet? So that's exploration part. We can see the regrets for different strategies with different iterations here. For instance, if you're greedy, you take a greedy approach, then your regret will increase a lot. If you're epsilon greedy, it means that you're greedy mostly all of the time, but once with the probability of epsilon, then you will try to explore something else, something that is less good than what you have what you have sampled already. And then you have other different types of algorithms, for instance, decaying greedy, decaying epsilon greedy, where you try to explore a lot at first, and then once you converge towards, I would say, a more fixed estimation of the different arms, then you can stop exploring or explore less and then exploit more. So different bandit algorithms exist, and they all differ in the way that the players will choose the arms. So that's exactly what I say here. That's here the stochastic bandit problem setting. You have a different set of arm, K, capital K, unknown probability distribution of rewards, and unknown mean rewards mu1 to mu k. So for each instance, the player chooses an arm among the possible arms, the environment reveals the reward, and then the player will have to update its estimation of the different arms. There are numerous algorithms and numerous settings and numerous variants of the different algorithms for bandits. You have, for instance, UCB, upper confidence bound. You could have XP3, which is exponential weights algorithm for exploitation, and you have sampling among the most known ones. I will maybe detail just tensor sampling because we have used that in the next result that I will show you. So tensor sampling, it's based on Bayesian statistics, meaning that you do an assumption on the environment, on what the reward might follow as a distribution function. And then more and more, as you get more samples, and you refine your own estimation, and you get a posterior that has a meaning that is more refined than the prior that you get in first stage. So for each instant, you would first estimate the values of the reward from a distribution. Could be Gaussian, it could be a beta distribution, could be whatever. But it's always better to have the conjugate distribution of the actual reward function that you will get from the environment. For this, we can have theoretical guarantees. Then you play the arm that is the argmax of this reward that you have sampled here, and then you observe the actual reward that follows a given distribution. That depends on the one. And then you can update the estimated distribution law parameters, for instance, the mu k, the mean and the variance, if you have chosen a Gaussian distribution, for instance. So that's the theoretical approach. You can use always heuristics as well, and you will lose the theoretical guarantees, but sometimes it could be more efficient, or it might be more adaptable to your problem. There are also structured bandits where you have the existence of a structure like F beta that's shown here, which doesn't depend on the arm that you choose. And it means that the reward that you get by playing arm KT doesn't depend on the arm played. It's a common structure for the arms. You can have linearly structured bandit, which is interesting because the structure is linear, and then you can go from a combinatorial problem to a linear one. And that decreases a lot the computing time. So this structure and how to harness that was covered in a seminar paper by Agrawal 10 years ago, about or so. and it's for linear constant sampling. So I will maybe detail the algorithm here. So first of all, you have to initialize your different estimation parameters, like the covariance matrix, the mean reward vector, or the covariance matrix more or less one, the identity matrix, and then the reward vector, a zero vector. Other intermediate function like j initialized at 0 as well. And then for all the different times, the time step, you initialize your estimated values of the reward for each arm k, so mu k here it's estimated in a mu till the mu vector for the value of the moment, of the different moments. Then you would play the arm that is defined as the argmax of the vector product of the internal features of the arm times the reward that you have sampled. And then you observe what is actually happening, what is the actual reward that you get, based here on the Gaussian distribution. And then you can update for the covariance matrix, the intermediate function, and then eventually the estimated reward function. So maybe after this introduction and how we have used it in our case study, so coming back to it, we assume that we had an energy community with on-site PV. So the PV is here, maybe higher up in the grid. You have this community here that could be small or larger. We have used two scales for the community, 55 EVs and 10,000 EVs. The community itself could be powered from the PV, of course. It will try to harness and to exploit this PV that is free for the community, but it could also be powered from the external grid with variable prices. And of course, we want to have EVs connected to this distribution network to charge efficiently, etc., but avoiding the congestion at the bus, at the transformer that is here. So for the mathematical formulation, we try to minimize the daily charging cost of all the EVs while ensuring some fairness. So that there is a big difference in terms of cost. Then it's not fair, so it's penalized. We want to avoid the constraints in current and in voltage, and we want to satisfy the consumers by having their stock, by targeting a stock per departure that is higher than a given value. So as I say, the agentification of the problem is based on the physical agentification, where line agents become line agents. They try to ensure there is no line congestion. The same thing for bus agents. PV agents themselves, they just communicate their PV production data to the EV agents, and the EV agents are the learning parts of this system. So the rest here, the other agent, PV agent, bus agent, line agent, they're the environment. They give information to the EV agents. EV agents make a decision, and then they can get a reward. And based on this reward, they can see the quality of direction. So for the line agent design, just to recall from what I said earlier, we have a criticality that is based on the line going through, on the current going through the line. It's 0 when we do not reach a certain threshold. It's it's higher than 0 if we reach a certain threshold, and then if we are above the maximum level, then it's higher than 1. So the criticality of the line, and the line itself, it can assess its own criticality, it can forward the criticality of other lines. For instance, it receives other criticalities from the environment, and it forwards the highest criticality to the rest of its neighbor. The bus agent work in the same way. And for the EV agent design, it's based on multi-array bandits. The EV tries to find the best combination of actions with the highest expected reward for charging. So just to summarize the EV agent process, each day is divided by n instants, which are the base arms. Each arms is binary, it's either you charge or you don't charge. Then each EV agent picks a combination SKT of charging intervals from the M base arms, on which it will hopefully have the highest reward. So that's the argmax of this combination of different arms times the estimated value of each instance at the vector. Then each EV charges at the selected interval if it's selected as part of this super arm. This combination is KT, and it receives a reward RKT from the environment. Then, following that, the estimated reward is updated, and after a few steps, you should have convergence towards the actual real reward occurring in the environment. And then you do that day after day or instant after instant, and then you can you reach on convergence at the end, but by going back always to step 3, where you try to pick at each instant or at each day a specific combination. I said we can do that every day or every instance because you can do real-time control here. You can just have to, if you pick up M base arm for each instant of the day, you just have to reduce the number of arms you have to play during the day to limit the number of charging instances. It's very similar. So the EV agent tries to minimize its threats. As I said, it's the difference between what reward you would have obtained if it had chosen the right optimal arm at every turn, minus what it has chosen eventually. So here, in that particular case study, we have used, included another part where the EV is actually also learning the PV production from the energy community. But it is optional. So at first, it tries to estimate the free PV energy before departure, the entire free PV energy before departure, without looking for congestion and all that. It will update the free PV energy step by step. And then it calculates the number of grid charging instants that it can have, that it needs to achieve the desired stock before departure. It tries to find the best estimated super arm to play, which is here sampled from a Gaussian distribution. It charts if the instance is part of the super arm. And then it observes a reward from the environment. So the reward here is twofold. If you do not have any congestion and you do not, the EV doesn't receive any criticality from the environment, in that case, the reward is 1 minus a normalized cost. So the lower the cost, the higher the reward. So the EV would go for the instant where the price is the cheapest. If, on the contrary, you have a congestion in the network, then the criticality received by the EV is non-zero. And in that case, they can receive a penalty that is embodied by the criticality they receive. Here, the criticality for the line and the buses, they are sent to only a subset of the different EVs that are present in the network. And those EVs that receive actually the penalty are sampled uniformly. And then the EV also receives the PV energy generation data from the PV agent. They update the charging strategy. And also, if we consider the learning of the PV for the generation, they can update the PV production forecast. That is, again, optional. So to go to the results of the first small case study, we had 55 EVs and we achieved convergence in 30 days. So we have evaluated all the performance of the agent at 30 days, over 30 days. Here, that's the normalized cost that we have used. So lower prices during the night and higher prices during the day, that's usual. So I show a lot of graphs and tables here, but we'll go one by one. So for the constraints, we can see here that here we have the uncontrolled strategy. And so we're higher than the congestion level. So we have congestion for the uncontrolled strategies. All the other strategies actually do not lead to congestion. So here that's for current, here that's for voltage, that's for the same. Not sure you see that well here, but here in blue and green, in green you have the MIRP, which actually tries to harness the energy during the day, so the PV energy, closely following the congestion limit here, but not exceeding it. And the same thing for the AMAS bandit-based meter that is proposed here in blue, I think, which is also harnessing as much PV energy as possible. And we had an intermediate strategy where we do not consider PV. We just want to have a look at lower, just the variable prices, just to have one step-by-step approach. We can see here, if no PV is considered, then the bandits and the AMS based method can actually harness the lower prices during the day. So that's for the constraints. For the level of optimality of the solution. Again, you didn't see anything here, right? So we'll try to explain it for you. we've tried to use the MIRP as the lower bound for the MIRP for the cost. The cost is zero. Let's say it's normalized. It's zero if we use the MIRP. If we use the AMAS-based and bandits method, then we have something that is close to 17% of increase in terms of cost. But then if we go to uncontrolled strategy, then we have 150% of cost in terms of increase. So our solution proves to be closer to a very kind of close to the optimal solution. In terms of fairness, to end with that, we've chosen this matrix for fairness, which is where sigma d here is the variance of the different charging costs for different EVs for a given day d, divided by the mean value of the charging costs for that particular day. So the centralized MIP solution managed to find a feasible solution where all the EVs would be fully charged, actually charged at the level they've indicated as their targeted SOC, and for which we have a fairness index of 1. So there is a feasible solution here that the AMAS bandit-based method manages to find. We also have full satisfaction of the EVs and a fairness index that is 99%. And so the small scale study was just here to play with and to understand a bit more of the bandits and all that. But then our target was a large scale case study with 10,000 EVs. For this, the same thing, we have conversions after 30 days. So there is a scalability really in terms of convergence. The constraint, the same thing, we just have a violation only in the uncontrolled strategy. And for the optimality, of course, here we cannot compare with the MIRP because it's not possible to have the solution with a centralized strategy here. It's too prohibitive in terms of computing time. But we can compare with here that's a maximum price that you would get, maximum cost you would get with the uncontrolled strategy. So that's our reference point. Everything is normalized here based on that cost. And we could see here that the average costs for the uncontrolled strategy over 30 days. And here, that's a bandit and AMAS-based cost over this same 30 days. So we can see here we have a huge decrease again in terms of cost. And the fairness index remains at the same, so 99%. So still, we have some scalability here. So for the proposed problem, we wanted and we managed to obtain in the end a system that is decentralized, that is able to tackle real-time operation, that is scalable, and also near optimal. Model-free because it doesn't need to have any model of the electrical network. It's able to tackle the stochasticity and it is fair. So we have developed this model. We have put the code in open source. We're still working on that as part of the national project that I'm doing. It's called Eden for Smart Grid. We have, among others, Orange, again, to help us with the bandit-based, EDF, and grid operator RSRD. We should have our website, official website, to launch anytime soon. So we'll provide some news on the projects from here. And for the perspective of this project, we want to further reduce the conversion speed. 30 days is nice, but it's not sufficient. And also we want to be able to consider very different external conditions because here in that part, the optimal policy remains the same regardless of the type of the day you're in, whether it's the weekend or weekdays, but you do not have the same density of electrical vehicles in the network, depending on the type of day, for instance. So that's something that we'll consider in the next work that we'll do, and we hope to submit that to PowerTech for next year. We also want to work on theoretical guarantees because that was the main point also to provide some comforting news to DSOs that maybe they can trust AI. So we'll keep continuing working on that, and then we'll work on cybersecurity as well. If you're interested, those are a few references for the work. And I think, yeah, I'm almost out of time, so I won't have time to maybe talk to you about AI-based security assessments. I think that'd be far too long. Maybe just a few words just to tell you that the work on security assessment has been done with different people, including Juan Cuenca, that some of you might know because he was a visiting researcher here 2 years ago, as he was doing his PhD with University College Cork. He's now an assistant professor in our lab, so we're very happy to have him around here, which also means that We are now hiring because we have a funding for 2 years for a postdoc to work on this AI-based modeling for faster security assessment. We have a flexible starting time. It could be any time between now and April. And we want to have a profile on both artificial intelligence and power system, but we can provide training in one of the fields if one is missing. One key point is that for the funding criteria that is mandatory is that the postdoc applicants should have 18 months outside of France. So maybe I've reached a broader audience that might meet the eligibility criteria here. But if you're interested, please come to talk to me and then we can discuss that. Maybe just to say a few words, we just wanted to have this topic developed because it's very complementary to what I said before. We have the learning agents that make decisions based on the reward coming from the environment, but the environment only, the reward for the environment comes also from power system simulation, for which we have about 86% of the time dedicated to just interacting with the power system simulator and doing the power simulation. So that's why we wanted to have some faster tools to assess whether the grid is safe or unsafe. And maybe I can come back to that later, but that's anyway. If you're going to the IGT conference next week, we have this paper presented. So I just maybe wanted to tell you about more on some upcoming projects in cybersecurity. We will be tackling the AI-based strategies and the challenge they have for power systems. We'll do a collaboration with the lab in France and Orange as well. The Orientation tool is still working on the same bandit-based method first and then expanding to other methods. And also with the University of Manchester, where we'll be looking at black house and things like this, very interesting things. It's a PhD that's funded by the ENS RAN and the China Scholarship Council. And the last project, also hiring Master 2 students to go for PhD thesis afterwards on biomethane and electricity sector crumpling, where we'll be using a thermal storage, a Carlo battery, as part of a project funded by the 2 French grid operator in gas transmission and distribution. So that's more or less it for this presentation. I'd like to take any question if you have, and maybe a special thanks for all the different organizers that have me hosted so well. And thanks to Umar, who's not here around here to receive my thanks, but Klaas Tulen as well, who hosted me yesterday, Gert de Konik, and well, of course, all the chapter in the IEEE Women in Power organization, and any one of you, actually, for your great welcome. Thanks.
Maybe I can start. So thanks for a nice work and nice presentation. So actually we are doing something similar in here in Energyville. So try to charge the EVs with the reinforcement learning. But yeah, I was wondering, so you said that you have the rewards coming from the critically something index that you calculate from the power flow, I assume.
Yeah.
The critical index. But how you make sure that you charge enough, let's say, energy that they request? Because if you don't do that, if you don't have a rule base above that system, so they try to charge less to not make the system in trouble.
Yeah, I think we always refer to we always look at let's say the small scale study first, because we want to see whether it's feasible to charge sufficiently and avoid grid congestion. Because at some stage there are no feasible solutions. It may exist that there are no feasible solutions. So in the extreme cases, we would avoid grid congestion and then not power the EVs sufficiently. But the thing is, we want EVs to be powered sufficiently if there is enough room for giving them power, right?
Yes. But my question is that, so, for example, you give a reward to the agent to learn how to behave.
Yeah.
But the reward, so if you don't penalize it, so they try to not charging the power, to not making a problem, then they don't get the penalty. So how do you solve that issue?
Yeah, I see. Yeah, true. Yeah, if you only use the penalty, then the agent would don't do anything. That's right. Yes. So you have to incentivize the agent to do something, and we do that by having a reward that is positive, where it's 1 minus the cost, a normalized cost. So that is why it's trying to charge, and then we stop that reward when it's sufficiently charged, actually.
Okay.
So it was somewhere in between.
The other question, how do you define your state space? So what is in your state space is that the time that you still have to charge, the time that you depart. What is your state space?
Well, for the AMAS bandit-based methods, we just act in real time. So it would receive a reward every time it charges well. Penalty doesn't charge as well because of congestion. And at the end of each day, it would receive a cost. It would assess whether it's sufficiently charged or not. And so it may happen that during the training phase, and it has happened during the training phase, that it doesn't follow the right path, so it doesn't start sufficiently charged, or it maybe creates congestion. But at the end, it should convert towards a case where at each instant of the day, it's only taking into account that instant of the day. Maybe what you can do is try to predict the different instants during the day ahead or along the day for a given horizon, and for which it would choose the number of charging instants. But the charging instant would be ranked by the estimated value of the different instants. And if there is congestion, I mean, let's say we have a case where you have the PV peak. So obviously you would have a huge value normally for that instant. But then you've tried to charge and you couldn't charge because there were congestion. So the value is reduced. And so based on that, you just have to know the number of charging instants that you need to charge your EV, and you have to rank the different instants. And maybe the different instant would be around noon, or maybe a little bit in the noon time for the peak production, but not for all of the EVs, because some of them have received a lot of congestion penalties. And so by ranking the different charging instants, then you can have the EV sufficiently charged at departure without leading to congestion, because they cannot level out the different values.
Maybe as the last question. So yeah, I agree that in ARM bandits it's very simple, but the problem is that you have to have the binary variable for the action space. But do you see that problem? How you can extend it to have the continuous power, and what kind of model we can use, because we then have the memory issue for that. If you use the continuous action space for different level of the power that we can charge.
I would see this question as twofold, because let's say you can say that maybe we would have different discrete values that are between 0 and the maximum power, and then you may have different steps. So here bandits would still be interesting. We will have how it works actually when we want to increase the computing time. That's one of the aspects we want to investigate, having different power levels. If we were to go to a continuous value, then maybe bandits, I'm not sure they would be the right tool to use. Maybe there are other methods that could be more suitable for that. But that's something that we need to investigate as well.
Even with a different level of the power, for example, let's say you can charge with a different level of the power, but it's not binary. But how do you define it for the bandit? Because bandit is using the arm or not using the arm. It's 0 or 1.
No,
but how do you define that?
Yeah, actually, by using a binary arm, it helps a lot by reducing the space, the search space.
Action space,
But if we can actually use different internal features, we call that internal features, and then we have to expand the vectors, but we can still have different. It's not only binary. I mean, binary is one of the cases for the bandits, and in the general case for bandits, it's not binary. It can even be continuous as well.
And you also have the assumption on the Gaussian distribution for the reward. If you go for the Q-learning, then you don't have that assumption. I think.
Yeah, well, for the sampling distribution, yeah, you can have many different assumptions as well. So we have to look into that. We are also going to different distribution methods.
Maybe question. Thank you for your nice presentation and also for explaining all these concepts used in energy management strategies. But my question will be more or less more not toward the distribution network, but more on the side of the EV itself. Have you tried to implement those energy strategies that you are developing, like in a real scenario? Because from my understanding, all these work is more or less numerical simulation.
It is, yeah, it is. And we actually want to implement that. We have, as part of the Eden for Smart Grid project that we have, we will implement that on a small platform that is developed at ENS. So it's a small-scale open source platform where we have different nodes to simulate a network. And we want to implement that as a first stage before maybe going further into the deployment.
Yeah, okay.
But yeah, definitely we have to go to real life, so step by step. But it's going to be just,
Yeah. Okay, good. Thanks.
I'd be more than happy maybe to have demonstrators maybe here elsewhere to test our strategies. So.
Maybe you should talk to class because you mentioned that you already met him. And he's working.
We're supposed to work as part of a project which wasn't selected, but maybe when it's not.
Yeah.
I haven't given hope.
Any questions online, maybe?
I don't know.
Because they don't change.